All right, IBAASL2. Today we're talking about the fundamental theorem of calculus, which sounds like a super big fancy thing, which it is kind of, but I feel like it's a very specific thing. I feel like it's so broad, but yeah, it's called the fundamental theorem of calculus. The first thing I want to say about this thing is that there's really interesting explanations as to how this fundamental theorem came up with, how somebody came up with it. It has to do with like trying to find the area underneath a curve, and then you can like split this into little like rectangles. You can try to build rectangles underneath it to try to estimate how much area is underneath this. And then if you take the sum of all these rectangles where the heights are touching the function, that you can get like an estimation for the area, but then you think, okay, but there's these little like leftover pieces that didn't get included. So then you can actually make those rectangles smaller. Instead of making them, a unit wide, you can make them like really tiny ones. And but even when you do that, you're gonna have like some leftover area. So there's some interesting stuff about the limit of like making those rectangles like infinitely small. If you're curious about it, I'm going to reference you to page 451 in your text as to why this formula works. But we are going to essentially just be using the fundamental theorem of calculus today, which states if f of x is a continuous function from a to b, so we have like a definite interval here, and capital F is the antiderivative, which we've seen capital F before, then if you are going to integrate from a to b, f of x dx, which is essentially finding the area underneath the curve. The way you do that is you find the antiderivative, and then you take it from a to b. So there's some interesting notation here. The a to b, this on the outside of brackets just matches up with the a to b here. Really, this is kind of just like a placeholder that you're like finding the antiderivative inside of f of x and then keeping this notation on the outside. And then that notation tells you that you should do f of b minus f of a, where these two are antiderivatives. I know we taught you the cheater way, how to do this all on a graphing calculator, but today we are going no graphing calculator whatsoever. So don't touch a calculator for any of this, and we're going to find exact answers. This is similar to how you guys will probably be tested on this eventually. We're thinking we'll probably have two different tests, one where there's no calculator whatsoever, and one where it's full graphing calculator. Do whatever you want on it. First problem. So we're going to evaluate each integral without using a GDC. So because it's a definite integral from 0 to 3, we first need to take the antiderivative of this. So the antiderivative of x minus 2, the power on x is 1, so you do 1 over n plus 1, x to the 1 plus 1, and then minus 2x. Remember, the antiderivative of just a coefficient, if you go backwards, is that coefficient with an x next to it. Then we're going to put the 3 and the 0 on the outside because we still haven't done anything with the 3 and the 0. The next step with this, according to the fundamental theorem of calculus, is you have to plug in b and a, and you have to subtract them from each other. So it's going to be the top first, then minus the bottom. What I mean by that is it's 1/2 3 squared minus 2 times 3, but then we're going to subtract out 1/2 0 squared minus 2 times 0. So this first part is the antiderivative, but the x replaced with 3. The second part is the antiderivative, but the x replaced with 0, and you subtract the two from each other. Now let's do some fraction work in here. This is 9 times 1/2 is 9/2. Then take away 6, and then 0 times 0 is 0, so we get take away 0. So this is 9/2 take away 12/2, which is negative 3/2. So that's our final answer. That's what the definite integral is equal to. And today you could certainly check that on a calculator, make sure you got the right answer. But once again, we're trying to do all the work by hand You can verify your answer, but don't just plug it into a calculator. Next up, we have a definite integral from 2 to 6 of 1 over m dm. Remember that the antiderivative of 1 over m is natural log. So this will be natural log of m from 6 to 2. So then we plug in the 6 and then subtract the 2. To be able to simplify this without a calculator, you need to remember your natural or your logarithmic rules, where if you have two logs being subtracted, they can be smushed together into one log where the two arguments are being divided. So the final answer to this is the natural log of 3. Next up, the definite integral from 0 to 2 of 4 EU du. First thing is that it feels a lot like u substitution because that u's in there, but remember this is just a variable. It can literally be any letter as long as this matches it, this would like with respect to u. So this is, well, the derivative of e to the u is just e to the u, and the 4 technically moves out front, but we'll just write it as 4 e to the u. From 0 to 2. So then you plug in the top thing, 4e squared, and then subtract out 4e to the 0. E to the 0 is just a 1, so this becomes 4e squared, take away 1. No, sorry, take away 4, because you still multiply by that 4. And you know what? If we're not using graphing calculators, this is as simplified as that gets. 4e squared take away 4. This is also a great example of a problem where if you did it on a calculator, the calculator would give you a decimal and not 4e squared minus 4. So, you know, if we're going exact answers and you give me a decimal, it's not the right answer. Okay, slightly more complicated problem. On the last round of testing, if I gave a problem like that, or I think I gave a problem similar to this, and a lot of people tried to do like the power rule on the separate parts and then multiply them or something like that, but we do not have an integration rule, a product integration rule where you can multiply those two things. So what we need to do is do some algebra before we do any sort of calculus. What I'm going to do is distribute the 2x squared to both of these terms to get 2x to the third minus 6x squared dx. Now I can certainly take the derivative of this. So this will be 3 plus 1 is 4, so this will be 2 over 4 times x to the fourth. And then 2 plus 1 is 3, so we get minus 6 over 3 x to the third. And we're going from negative 2 to positive 2. So, well, first of all, we can clean that up. Let's clean it up. Now, when we plug it in from 2 to negative 2, you do 1/2 2 to the fourth minus 2 cubed, but then subtract out all of 1/2 negative 2 to the fourth minus 2 negative 2 cubed, and then close your parentheses. So it's like with 2 plugged into it, and then subtract negative 2 plugged into it. Let's do some math on that. 2 to the fourth is 16. So we get 1/2 times 16 minus 2 times 8, and then subtract. Negative 2 to the fourth is positive 16, so we get 1/2 times 16 as well there. And then a minus 2, and then a negative 8, because when you cube negative 2, you get a negative number. this equals 8 minus 16 minus 8 plus 16. 8 minus negative 16 is negative 8, and then the 8 and 16 together are 24, so this is minus 24. I believe this whole thing is negative 32. Let's check the book. Yep, we nailed it. Sweet. Now, you guys, there's two ways you could go with this problem. You could FOIL this all out. You could cube 2x plus 1 and then just use your straight power rules. But cubing something is a lot of work. I'm going to recognize that this looks like a backwards chain rule because there's an inside function. But notice there is no 2 on the outside, so we're going to have to engineer a 1/2 in there. So when we take the antiderivative, this will be 1/2 times 1/4 2x plus 1 to the power of 4 from -1 to 0. Just making sure we're all good. Yeah, we're on track. Okay, so we'll do a little cleanup first, that the 1/2 and 1/4 can become 1/8. And that's really the only cleanup I see that we can do. Still have 0 to -1 on the outside. Then we're going to plug in 0, so we get 1/8, 2 times 0, plus 1 to the power of 4, and then subtract out 1/8, 2 times -1, plus 1 to the power of 4. 2 times 0 is 0, plus 1 is 1 to the 4th is 1, so we get 1/8, and then we're going to subtract 2 times -1 is -2, plus 1 is -1 to the 4th is positive 1, so we get minus an 1/8. Wow, thought that was going to be more complicated. It was all 0. Next problem. First, I'm going to rewrite that as 4x plus 5 to the 1/2 dx. Recognize that this is a backwards chain rule. You could use substitution if you want, but the inside is linear, so really that just means we're going to have to put a 1/4 on the outside because we're missing a 4 coefficient derivative of the inside. So this will become... well, we need to have the 1/4, and then it's going to be times 1 over n plus 1. So 1/2 plus 1 is 3/2. So this will become 1 over 3/2. 4x plus 5 to the 3/2. And then we're going from 1 to -5/4. Okay, cleanup time. Right here, the 4 times 3/2. 2 goes into 4 twice. 2 times 3 is 6. I believe this is 1/6 on the outside of 4x plus 5 to the 3/2. And we're going from 1 to -5/4. All right, I think we're ready to start plugging it in and see what happens. Hopefully things simplify well and it doesn't get too gnarly. We'll find out. 1 over 6, 4 times 1 plus 5 to the 3/2. Oh, interesting. Okay, just seeing where this is going to go. And then we subtract out 1/6. 4 times -5/4. Oh, it's nice that those 4s are going to cancel out. Plus 5 to the 3/2. Now let's start to simplify. I'll let that 1/6 hang out, and then inside we get 9 to the 3/2. And then here we get minus 1/6. Now 4 times -5/4 is just -5, but then -5 plus 5 is 0, So we get 0 to the 3/2. That's nice because this whole part's going to go away. So really, we just have to do 1/6 times 9 to the 3/2. Now, you might be looking at that and being like, Mr. Jolly, how on earth am I going to do 9 to the 3/2 without a calculator? Remember or recognize that 9 is a hot number. It's 3 squared. So you can rewrite this as 1/6 3 squared to the 3/2. And then power of a power, you multiply. So this becomes 3 to the cube because the 2's cancel out. So this becomes 27 over 6. Oh, that can be simplified. They're both divisible by 3. So, what was that? 9/2? Let's check the book. We did it, you guys. 9/2. Last problem. We're going to do this definite integral. Looking at this, you might be intimidated or you might be prone to making a mistake because we don't really have like a quotient property of integrals. Some people might try to just say that this integral is just itself, but that's not quite true. Oh, forgot the dx on the end. What you're going to do is rewrite this. You're going to split it into e to the 4x over e to the 2x plus e to the 2x over e to the 2x dx. Now, this is a giant 1, so that's nice. And then here, when you have the same base, you can actually subtract their exponents. So no calculus happening yet, but this will become e to the 4x minus 2x plus 1 dx, which is e to the 2x plus 1 dx. Now it's in a much nicer form where you can take the integral. So we'll just take the integral of both those parts, and this will become 1/2 e to the 2x. Don't forget we're doing a little backwards chain rule U substitution because there's a 2 inside there, so you get to balance it with a 1/2. 1/2 e to the 2x plus x. And we're going from 1 to 3. So we do 1/2 e to the 2 times 3 plus 3 minus 1/2 e to the 2 times 1 plus 1. Now let's clean up. 1/2 e to the 6th plus 3 minus 1/2 e squared plus 1. Distribute that negative. Then, let's think. If we have... Now, there's really not a whole lot we can do to clean this up except for the plus 3 and the negative 1. I know it feels like you should be able to do something with these, but that's kind of like saying that like x to the 6th and x squared should be able to be combined, which you can't. They're very separate terms. So we're going to say the final answer is 1/2 e to the 6th minus 1/2 e squared plus 2. Does the book agree? They do. All right, you guys, that's all I have for us for today. Please get at me with those homework problems if you are struggling.